Hi, my name is Vincent, and today I want to take you all through the second half of the June 2019 Geometry Regents. The first half of this video has already been recorded, that you could find it in the description below, along with a PDF copy of this exam. So question 25, we're trying to determine if triangle ABC is congruent to triangle A prime, B prime, C prime, and the transformation that occurs here is a dilation with scale factor 1/2. So real quick, if I scale this original triangle down by a scale factor of 1/2, the resulting triangle is going to be smaller than this, so they can't be congruent. So right away, no is the answer, but in order to get full credit here for a question like this, you need to explain your answer, which means you need to write a sentence to get full points. So we could say no, they're not congruent, because if we dilate with a scale factor of 1/2, the resulting triangle is the same shape, but it's smaller in size. So this would get us full credit. Now for question 26, we want to determine the area of triangle PQR, and it has vertices shown here. So my advice, it makes a lot of sense in questions like this to plot them, because it brings the question to life and gives you a better idea of what to do. So in this situation, if we look at the diagram, these lines PR and QR are perpendicular. So since they're perpendicular, we could just find the length of PR and QR and then use area equals 1/2 base times height. Now the reason why we know for sure these are perpendicular is we could look at the slopes. So if I calculated the slope of QR, I could do it the long way and use the formula. So I would do 5 minus 1, the difference in the y values, divided by the difference in the x values. And in this situation here, we would have 4 over -3. But now to find the slope of PR, this line segment here, if I count the boxes, I'm going, let's see, 4, 5, 6, 7, 8 boxes to the right, and I'm going up 1, 2, 3, 4, 5, 6. So I'm going over 8 and I'm going up 6. So that tells me that the slope of line segment PR is essentially I'm rising 6 and I'm running 8, and this reduces to 3/4. So since my slopes are negative reciprocals of each other, that tells me that PR is perpendicular to QR, which means that I could just find the distance of these two and use the area of a triangle formula. Now, I personally like using the method in blue here, because when it's in this form, to find this distance, I could just use Pythagorean theorem, or I could recognize that this is a 6, 8, 10 right triangle. But if I check this out, 6 squared plus 8 squared will equal 100, which the square root of 100 is 10. But now let's say I want to find QR using the distance formula, since I used the formula to find the slope. Then the distance for QR would be, I would do the square root, and now we're doing the difference in the x value, so I'm doing 6 minus 3, and we're squaring that, plus the difference in the y values, now we have 1 minus 5 squared. And this is going to simplify to 3 squared is 9, -4 squared is 16, and the square root of 25 is 5. So QR is 5 units long. And we said before from our diagram that PR is equal to 10. So if I want to find the area of the triangle PQR, I'm doing 1/2 base times height, and the base is 10 along PR, and then the height is 5. So if I work this out, it's going to be 25 units, and that's my answer here. The second option is I take the triangle PQR and I inscribe it in a rectangle. So I draw a horizontal line at the bottom, the top, and vertical lines at the left and right. And what I'm going to do is, if I find the area of the rectangle and subtract out the area of these 3 right triangles, that's going to tell me the area of the triangle in the middle, PQR. So I just have to count the boxes, but this red triangle here has dimensions 10 by 5, so the area is 10 times 5 is 25. The purple triangle is a 3 by 4, so the area is 6, and then this last triangle here is an 8 by 6. So if I use the formula, the area is 24 square units. So if I want to find the area of the yellow triangle, the area of the rectangle is 80 because it's 10 by 8. So I'm just going to do 80 minus the sum of these three areas, and I also get 25. This method might be the best because it works even if this is not a right triangle. So this is usually preferred for those specific cases. Now for question 27, we have a word problem, but what we need to be able to do is read this question and translate it onto a diagram. So we have a support wire reaching the top of a pole, and the wire goes from the top of a pole to a clamp on the ground, and they're telling us the clamp is 10 feet away from the base or bottom of the pole. So this distance here is 10 feet. And we know that the support wire makes a 68-degree angle with the ground. So the wire and the ground have a 68-degree angle between them. And we want to know what is the length of the support wire to the nearest foot. So we'll call this X. And we're assuming this vocabulary here, the pole is perpendicular to the ground, just says that it was built well, and we have a right angle here. So just be careful setting this stuff up, because once you set it up, the math isn't too bad. Then you just have to identify your trig function correctly. So if we use the mnemonic SOHCAHTOA, we know the side adjacent to the 68-degree angle, and we want to find the hypotenuse, so we're going to use cosine. So now if I use the formula, cosine of 68 degrees is equal to 10 over x. All I'm going to do is solve for x, so just be careful with the algebra when the x is down here. If I cross multiply, I'm going to have x times cosine of 68 degrees. And this is equal to 10 times 1. And now to solve for x, we're just going to divide by cosine 68 on both sides. And in this question, we're rounding to the nearest foot. So just make sure we have a whole number for an answer. So x equals, and now we just got to type this in. We have 10 divided by cosine of 68. Please make sure you're in degrees. See up top it says degrees. That's a good thing, because if you're in radians, it will ruin your day. And now we're rounding this to the nearest whole number. So the 6 to the right of the decimal tells us to round up to 27. So our final answer to this question is 27 feet is the length of the wire. Let's, make that a little neater, 27 feet. All right, now moving on. Question 28, we have to find the area of the shaded sector, AOB. So this is what we want to find, is the area of this section here. And we're told that the arc is 72 degrees. Now the concept that you need is that the central angle is equal to the measure of the arc that it intercepts. So now to find the area of the shaded region, another thing we need to know is that the area of a circle is pi r squared, but we're only taking a fraction of the circle. We're only, and the way we find out what fraction we're taking is we look at the central angle and we divide it by 360 degrees, because if we covered 360 degrees, that would be the entire area. So it's this part, 72, over the whole, and we're going to multiply that by the area of the circle. So we're going to multiply by pi r squared. And the radius in this case is 10. So then all we have to do, and we're leaving our answer in terms of pi, so don't write it as a decimal, because that would be an annoying thing to lose points for. So we just expand this a little bit. You could just type all of this in the calculator if you don't feel like doing mental math. Like I would just type in the numbers 72 divided by 360, and then I'm multiplying by 10 squared, which is 100. And you see I'm going to get 20 pi. So to simplify this, this is just 20 pi. If you wanted to show the work by hand, this reduces to 1/5, and 100 divided by 5 is 20, so also 20 pi. Now for question 29, we have two congruent triangles. ABC is the original and STU is the image, because ABC is mapping onto this one, and we want to describe a sequence of rigid motions that gets us there. Now if we identify the coordinates here, for point A, the coordinates are -2, 4, and point S is -4, -2. So if you think carefully about this, if I'm sending the point -2, 4 to point S, which is -4, -2, well, how do I get there? I could do a rotation of 90 degrees about the origin, because my y value changes signs and then it flips. So we could actually do this in one rigid motion, a rotation of 90 degrees, counterclockwise about the origin. Now, a few things. For one, you absolutely need to include the degrees that you're rotating, the direction you're going, and the point that you're spinning around. So if you exclude that, you're going to lose out here. If I have a lot of time for this test, I would check out points C and points B to see that they map to the other two. But a cool way of showing that this works out, not something that you would do with the test, but just some exploration of the concept. See, if I make a circle from the origin to point A, and then I connect the origin to A, and I connect the origin to S, see how it makes a right angle. And if I do that again, now let's say I make the circle go from the origin to point T instead, see how B and T connect, and if I draw the lines in, I'll have another 90-degree angle. So this is just extra confirmation that this sequence will work. Okay, for this question here, we have a right triangle, and we're drawing an altitude in from the right angle, forming another right triangle. So for these questions, one thing that's really important to note is that all three right triangles in this diagram are similar. So we need to be able to set up a proportion here. Now, the goal is to find the length of RQ, which is this segment here. So if we call this segment, we give it a name, like we'll just call this one X. We're basically just finding the value of X. So the two triangles that we want to look at here is this right triangle, which I'm highlighting here in blue, and we'll just rewrite that because that kind of got hidden, and the original right triangle, which is what we'll highlight in green. Now when you're setting these up, there's a few different approaches, but I like to just think the short leg is the one that's visually like shorter than the other. So I have the short leg, the long leg, and the hypotenuse. So when I set up my proportion, let's look at the blue triangle first, so PQR. The short leg is not labeled, but the long leg is X. So I'm going to compare X to 15, and the names of those relative to the triangle is X is the long leg and 15 is the hypotenuse. So when I set up a ratio for my green triangle, I'm comparing the long leg to the hypotenuse. Now this is clearly the short leg, so the long leg in the green triangle is 15, and the hypotenuse labeled down here is 17. So when I solve this, we'll have our answer to the question. So I cross multiply, 17 times X equals 225, and we want to round our answer to the nearest tenth. So we're going to divide by 17, and we have X equals, and now we're just doing 225 divided by 17. And to the nearest tenth, this is 13.2. So our answer to this question here, we have X equals 13.2. If you want to be really safe, you could just say RQ equals 13.2. So you're labeling it according to the question, but that's usually not something that they're going to take a point off for. You should be fine here saying X equals 13.2. Now, one other detail to mention, another way of interpreting this question is that since the blue and green triangles are similar, that means their trig ratios have to match. So if I, let's say, look at cosine of R, we'll do this for the blue triangle first. Cosine of R would be X over 15 because X is the leg adjacent to R and 15 is the hypotenuse. But in the green triangle, cosine of R, the adjacent side in the green triangle would be 15 over the hypotenuse 17. So you see how it gives us the proportion we had before? This is just a second way of interpreting this question that will make more sense, because the more ways you could understand it, the better off you'll be. But we don't need this in our actual solution. All right, for this construction question here, we want to construct an equilateral triangle inscribed in circle O. So the strategy I want to go with is to use the kind of like the same technique for constructing a hexagon. So what we're going to do is we're going to measure the length of the radius with the compass. And to show that we use this value, we'll just draw in an arc. And now what we do is we move the compass to point A, and we swing an arc so that it hits the circle. And we just continuously move the compass to the intersection point that we just make. We don't change the length of the compass, and we keep doing this. and we should generate 6 intersection points from like, you know, all along the circle. So we're going to just do this again. And it's very important for these kind of questions that you show the arcs, because if you just kind of do it by hand and you just eyeball it, they're not going to give you full credit. So we have one more to do. And let's see, so we place it at the intersection point. We do this again. And now we don't have to do this part, but if we want to show, if we place the compass here, you can see that it's going to bring us right back to point A where we started. But now be careful. Don't connect everything, because it's asking us to construct an equilateral triangle, not a hexagon. So we're not going to connect all 6 points. We're going to skip a point. Because if I connected this one to this one to this one, it wouldn't be equilateral. So we're going to connect this point to this point and then to this point. So we get our straight edge. You guys would have to use a ruler unless you're doing it on the computer too. But I connect this point here, and I connect this point here, this one here, and we have an equilateral triangle inscribed in circle O. All right, now these are the 4-point questions coming up, the 32, 33, and 34, so there's a little bit more to do here. So for this question, I highly recommend that you plot these points, and the goal here is to prove that this quadrilateral is a trapezoid. So for one, you have to know what it means for a quadrilateral to be a trapezoid, and a trapezoid is a quadrilateral that has exactly one pair of parallel sides. So the way we're going to show that these sides are parallel, and that's why we draw it out, because it's visually obvious, AD and BC are the parallel sides, is we have to analyze the slopes of all the sides involved here. So we're going to show that AD and BC have equal slope. So if we calculate the slope of AD, we're just subtracting the y values. We're doing 6 minus 0 divided by -1 minus 1. And that works out to -3. And next we'll find the slope of BC. And when you find the slope of BC, you also get -3. So right away we have matching slopes. But I'm also going to find the slope of the other two sides involved. So we find the slope of AB, and we get 1/2. And then we find the slope of DC, and we get -1/5. So now that this is accomplished, if we stop here, this is a common mistake I've seen over the years. We're not going to get full credit, because we actually, if we have to prove this in this question, a proof involves, you know, more than just showing math. We have to actually write a sentence to get full points. So now we just have to explain what this all means. So since the slopes of AD and BC are equal, this tells us the two lines are parallel. Slopes of AB and DC are completely different than all the others, so they're not parallel to any of the sides in this quadrilateral. So since we only have one pair of parallel sides, this tells us that ABCD is in fact a trapezoid. For the rest of this question, because it is a 2-part question, now we have to use this definition that an isosceles trapezoid is one that has congruent diagonals. Well, this is Riley's definition. This is actually a theorem that could be proven, but we want to use this definition to show that this trapezoid is not an isosceles trapezoid. So really what we have to do here, if we're going to use Riley's definition, is we have to show that the diagonals are not congruent if this is not going to be isosceles. And just in case you don't know what an isosceles trapezoid is, it's one where the slant sides A, B, and DC are congruent. But in this case, they're not going to be. But we're using Riley's definition for this case. So the diagonals are BD and AC. So if we find the length of the diagonals, the length of BD, if we use the distance formula, the length of BD is going to be square root 68. And if we find the length of AC, it's going to be longer. It is going to be square root 98. So now, once again, we are writing a proof. So we actually have to write a sentence. This would not be enough to just show the math. So to conclude what we have here, we could just say, since they're not equal in measure, the diagonals are not congruent. And if the diagonals aren't congruent, we can now conclude ABCD is not an isosceles trapezoid. All right, question 33, we're finding the volume of the swimming pool, which is in the shape of a cylinder. So go ahead and, we'll draw out a pool in the shape of a cylinder. And we're given the dimensions. Now be careful here, we're given the diameter. So if we want to find the radius, we're going to take 6.5 and divide it by 2. So this tells us the radius in feet is 3.25. We're also told that the height is 12 inches, but once again, we have a problem. Feet and inches don't match, so we'll convert this. 12 inches is equal to a foot. And the pool is only being filled to 2/3 of its height. So if we look at this picture here, like this much of it, about, like that's about the 2/3 mark. Like that's how much water we have. So we have to take that into account when we answer this question. And the formula that we need is the volume of a cylinder is pi r squared times height. But the volume of the pool, this is where we have to be careful. If the pool is only filled 2/3 of the way, we're going to multiply the volume by 2/3 because we're solving for the volume of water, not the volume of the pool itself. So we're going to do 2/3 times pi and the radius squared, and then times the height. And the radius, we said before, was 3.25. Let me just make a little more space. Wrote too small. So let's see. 3.25 feet. That's being squared, and we're multiplying by the height, which is 1 foot. Now I'm writing the units in because it really helps us understand the next part of the question. But here we're rounding to the nearest cubic foot. So we're just going to type all of this into the calculator. So we have 2/3 times pi, and now we're going to multiply that by 3.25 squared, and then multiplying that by 1. Now we're not going to write the times 1 at the end, and we're rounding to the nearest foot, so we're going to round to the whole number. So after the decimal is a 1, so we're rounding down to 22. So for this, we have 22 cubic feet is our answer to the first part. Now, once we answer this, the next part isn't so bad. We just have to be careful. They're telling us that 1 cubic foot equals 7.48 gallons of water. So we just, to find out how many gallons we have in the pool, we're going to take our answer. So the number of gallons, we're going to take 22 cubic feet, and we're going to multiply it by the conversion factor, 7.48 gallons for every cubic foot. So divided by cubic feet. So since these are basically equal quantities, we're just going to multiply the volume by the density, and it's going to tell us how many gallons we have. And the reason why I like to show it this way is because cubic feet over cubic feet cancel. So then to answer this question, all we have to do is just multiply 22 by 7.48. So now we can just do our answer times 7.48. And we get to the nearest whole number again. That's going to be rounding to 165. So this is 165 gallons. Now, one thing that I should mention, you may have noticed that I didn't use our rounded answer from before. I used the true decimal answer, but let's say we did use 22 and multiplied that by 7.48. We're still going to get the same answer. And when I looked at the sample student responses to this, both students got full credit whether they used 22 or the 22.122. So either way, you're going to get 165 and you'll get full credit for this question. So for question 34, we have this word problem, and there's a lot going on here, but the diagram tells us everything that we need to know because what we're trying to do here is solve for x. And the diagram has everything. It's just this guy, Nick, staring at a windmill, and these are the dimensions of like where, you know, he's standing and what he's observing. So if we want to solve for x, the way we're going to go about this is we're going to consider the entire height of the windmill from the bottom. We'll call that height z. And we want to consider the distance from the ground up to, we'll call that like the axle, which is like the center where the blades all join. We want to measure that height too and call it y. And the idea is if we're trying to solve for x, we could note here that x plus y, so x plus y is equal to z, which tells us that x is equal to z minus y. Oops, let's try writing that again. X equals z minus y. So what we're going to do is we're going to consider this right triangle here built with a 30-degree angle, and then the bigger right triangle which uses the entire 38.8 degree angle. So let's say I separate the triangles. Like this is the small one. So this is the one here this is y. This is a right angle. This is 30 degrees, and this is 440 over here. And then in the bigger right triangle, we would call this Z. This is still 90 degrees. The base is still 440. And the angle this time changes to 38.8. So just drawing it separate because it might make it easier for you to see how we're setting up the trig ratio later on. So the mnemonic that helps us choose our trig ratio is SOHCAHTOA. In both of these triangles, we're looking for the opposite side, and we know the adjacent side, so we're going to use tangent for both of them. So we're going to use it for the, to find y first. So we'll have tangent of 30 degrees is equal to y over 440. So to solve for y, we're just going to cross multiply, and this tells us that y equals, so now we have to use the calculator. We're doing 440 times tangent of 30. And we record this value. I'm going to record a bunch of the decimal places, and we'll round at the end. So 254.0341184. And now we're going to repeat this process to find the value of z. So now this time around, the angle is going to change. We have tangent of 38.8 degrees is equal to z over 440. And then to solve for z, we're going to cross multiply just like before. And we have z equals, so now we're doing 440 times tangent of 38.8 degrees. So that's what we're getting here by multiplying those. And we're going to record this value. We have 353.7690827. Okay, so now to close this out, if we want to solve for x, we said we're going to take z and subtract y from it. So what we could do is we could just take our answer for z and we're going to subtract y. Now you could type that in again, or if you're you don't want to do that much stuff, just go up to it, hit enter, and it'll type the y in for you. We hit enter, and now this tells us that our value of x is equal to, and we're rounding to the nearest foot, so whole number we're rounding to, 99.7 rounds up to 100. So this is going to be 100 feet. Okay, so this is the last question of the test. This one is worth 6 points. And anytime I have to do a proof, what I like to do is read the givens, translate it onto the diagram, read the proof statement, and then develop a strategy from there. So we have quadrilateral MATH, quadrilateral math. That just tells us these are all connected. We have HM is congruent to AT, so this we could label with tick marks. We have HT is congruent to AM, so we could label these two sides with double tick marks now because they're a different pair of congruent sides. And now we have HE is perpendicular to MEA, so we could draw in a right angle here and here if need be. And we have HA is perpendicular to AT, so we have a right angle in this corner as well. And the goal is to prove that the product of these two segments equals the product of these two segments. Now, this proof statement is reminiscent of the idea that the product of the means is equal to the product of the extremes. And this terminology exists when we're talking about proportions, usually coming from similar triangles. So I'm going to define all this vocabulary in a moment, but this tells me that our strategy is going to be to show that we have a pair of similar triangles, to set up a relevant proportion involving those segments, and then to use the results, the product of the extremes is equal to the product of the means, or vice versa. Either way we could say it. Now, this vocabulary, the extremes refer to the end values in a proportion in this colon notation, and the means are the inner terms. So in fraction form, the means are located here at the denominator of the first fraction and numerator of the second fraction. So if I want to set up a proportion involving these means and these extremes, I'll color coordinate here, but the means are TA and HA. See how they're showing up in corresponding locations here. And then the extremes, we'll write in red, are HE and TH. Now, since I wrote TA first and then HA second, I'm going to write HE first and then TH second. But we're going to see in a moment that this is going to correspond to the similar triangles that we have in this diagram. Now, some things that we could draw from the givens is that since opposite sides are congruent, this quadrilateral is a parallelogram, which means that alternate interior angles formed by the transversal are congruent. So I could say that angle THA is congruent to angle HAE over here. So now, since this triangle here and this triangle here have two pairs of congruent angles, they have a right angle between them and they have the angle marked in purple, these two triangles are similar. It may not be visually obvious because of how they're situated. So I'll just show here that we could separate these. Hang on, one more try, and yep, there they go. So if I drag these triangles out, you could see that these two triangles are similar. Now, I know they're not facing the same direction. I could flip them around, but these two triangles are, in fact, similar. So if I do this, see how if I face them this way, this one is a scaled up version compared to the other one. So if I look now, HE over TA is comparing this vertical segment to this one is equal to the hypotenuse HA in this triangle to TH in this one. So now for the proof part, the first thing we write are the givens. So we're just going to restate the givens. And now the strategy is show the triangles are similar. So that means we have to establish angle-angle similarity. We need to say in our statements that two pairs of angles are congruent. So what we have to say to show that the two right angles are congruent, first we have to define them as right angles. So we're going to say that angle HEA and angle TAH are right angles. And the reason, perpendicular lines form right angles. That was in the assumption we underlined in green. Now we could say these two angles are congruent because all right angles are congruent. So far we've only established one pair of congruent angles. We need to establish that the angles highlighted in purple are also congruent. However, if we say that next, we're going to be in trouble. At no point did we establish that this is a parallelogram, so we have to state it. MATH is a parallelogram, and the reason why it's a parallelogram is because both pairs of opposite sides are congruent. So once you establish that it's a parallelogram, it would be a mistake if we just jump into this right now and say the angles are the same. First, we have to say that these lines are parallel, because the only way you could have alternate interior angles is when you have parallel lines cut by a transversal. So we're going to say that HT, line segment HT, is parallel to line segment MA, and the reason being opposite sides of a parallelogram are parallel. Now we could finally establish these last pair of angles as congruent. So angle THA is congruent to angle HAE. These two angles are congruent because alternate interior angles formed by parallel lines in a transversal are congruent. So now we've just established enough to show that these two triangles here are similar triangles. So in the next statement, we could say that triangle THA is similar to triangle HAE. And see how we're writing the letters in corresponding order. That's important. And the reason is angle-angle similarity here. So once you establish the triangles are similar, then we could set up the relevant proportion. Now we could say what we said over here, HE over TA is equal to HA over TH. And the reason for this, corresponding sides of similar triangles are in proportion. And now finally we can make the concluding statement, which we knew the reason before we started writing anything. And the product of the segments are equal because the product of the means is equal to the product of the extremes. Okay, well, this is going to conclude the June 2019 Geometry Regents. If you found this helpful, please click like and subscribe below. If you have any requests, please leave it in the comments section, and thank you for watching.